Cool. Can you see my slides okay? Cool, thank you. So yeah, hi everyone. I'm Fergus and my talk's on deep learning to improve patient outcome on the hospital ward. So I'm a first year PhD student working with one of the doctoral training centers run by the computer science department. And its research is focused around tackling data-driven problems, but with humans really at the center. So my domain is obviously clinical, and I'm really trying to consider how can I develop these models with clinicians and patients in mind to get kind of the most use out of them. So in this talk, I'll discuss kind of machine learning in healthcare a bit more generally. I thought I'd just give some nice examples of current research. And I'll discuss challenges associated with my research, and finally talk about the specifics of what I've been doing for the last few months, which is time series classification and using generative models for generating fake data. So I'll first talk about machine learning in healthcare. I thought I'd give some nice examples of research that I found. The first being medical imaging. So deep models have formed the kind of state of the art for medical imaging problems, for image analysis problems, sorry, for many, many years now. You might have seen phenomenally powerful image classifiers, and they can be applied for medical imaging. So this diagram's really nice, and it shows some output of an MRI scan where, given a dose of some contrast agent, a deep learning model is able to take an image which has a dose 10% of the size of a standard dose and increase the contrast for a specific area to make it look like that of the standard dose. So for this specific example, that would mean this MRI technique could be used for a much wider range of patients, potentially much safer as well. So this can be used particularly for stroke, psychiatric disorders, epilepsy. Brain imaging has a lot of different areas where it can be applied. And another similar example is taking the same kind of technique where we have a image of what would be a normal dose, 100% dose of some contrast agent, and given an image of a much smaller dose, so in this case 3%, we can synthesize and improve this image to create one that looks very, very similar to that of a 100% dose. So I just think these applications are really cool, and these kind of imaging techniques also translate to what I'm doing when I'm looking at time series. So another branch of research which is particularly applicable to my project is sepsis detection. So sepsis is defined as a dysregulated host response to infection. And what this means is that when a patient does have an infection, if their body doesn't necessarily know how to deal with it, it starts to kind of fight itself. And this can lead to organ dysfunction and many other complications. But the key problem is that sepsis is very, very hard to define and detect. So systems that can detect this earlier are extremely useful. So this particular model uses a neural network with 3 hidden layers, and they're not particularly wide. They have 256 nodes. So the takeaway is that this model is quite simple and it performs fairly well. It has an AUC metric here of 0.86, so it has a pretty good true positive rate, which is very good in this domain. And if we do get early detection for sepsis, what it means is that the interventions can be done quicker, which is key in improving patient outcomes and improving these trajectories. Furthermore, these kind of models can be developed to be more interpretable and help empower clinical decisions. So a lot of the current machine learning research that's done isn't necessarily implemented within a clinical setting. It's extremely hard to put these models into a clinical workflow. So designing dashboards, designing systems like this one shown here, where a clinician will be displayed with 3 different views, one with the risk with 3 different risk scores, where this pink line is the predicted risk score from the model, and the red line is the risk score for sepsis given a specific sepsis definition. They then have some metrics from the which would commonly be taken in an ICU setting, like heart rate, respiratory rate, temperature, oxygen saturation, these kind of things. And then at the bottom, there's some causes of particular changes given a time period. So you can see at the start, sort of temperature is causing the most change. And then as complications arise, surgery, ventilation, respiratory, all of these are accounting for this big change. But what we see is in this top section, this pink line is increasing before the red line. So we're seeing that this sepsis prediction is actually working, maybe 6 or 8 hours. It's hard to see from the diagram at the bottom, but let's say 6 hours before this sepsis event actually occurs, this pink risk score, has shown improvement. So these kind of systems being designed would really help to empower a decision and could potentially be implemented within a clinical setting. So I'm working with electronic health records, and these consist of diagnosis, medication, treatment plans, lab results. For me specifically, I just have ward data for patients in a variety of different hospital wards. There's lots of publicly available electronic health record data, but it's not all particularly useful or relevant to my domain. So there's a big ICU data set, there's a big genomics data set, there's an open access COVID-19 data set. And while this is all really good, it's challenging for machine learning researchers in a lot of clinical domains to actually have access to good data. So private medical data obviously has strong regularization in accessing it. Even when it's de-identified, it can't just be made publicly accessible, which leads to sort of big discrepancies between research and what researchers can use. So one solution could be utilizing machine learning to generate synthetic data, which we may be able to bypass this regularization by generating good synthetic data sets that can still be used by the machine learning community to train extremely good models. So I think it's an interesting approach to consider. So I'll talk briefly just about some of the challenges of this domain and the challenges I've been facing with my own research. So there's lots of challenges associated with the data. So missing data is a problem for many machine learning researchers, but it seems that in the clinical domain, this is more prevalent. So between hospitals, there's not necessarily standardization of how certain data is collected. For me, I'm analyzing patient wards where data isn't collected as often as it would be for a patient in the intensive care unit where their vitals would be constantly monitored. Researchers who do have access to private data set and may be publishing their findings on that private data won't be able to have their analysis fully replicated by other researchers, which can be a big problem in validating the integrity of their research. These data sets often are very sparse as well, where for a very wide range of input features, there may be thousands of different medical events input to a model, the majority of them could be zero. And this leads to very, very challenging training processes where models really struggle to actually understand the correlations between features and then inevitably struggle to learn anything at all. There's also often a lack of positive examples. So in my case, this would be patients that do develop sepsis. So in a data set, it could be that only 10% of the patients actually develop sepsis, which means that models can easily become biased to only classifying the patients where sepsis doesn't occur. So this also leads to different training processes and different training schemes needing to be devised. Poor labeling is also very common where in my case, I have no sepsis labels, so I need to generate these myself and come up with criteria that I think is suitable and that generates a good enough cohort of patients for a model to train. And this can also be done in many cases in conjunction with clinicians. You see a lot of medical imaging research where the clinicians will verify certain areas of an image, or they'll be able to help build up this data set. And when developing anything clinical, you're making critical decisions. So if you are training a model to meet some kind of evaluation metric, at what point is it actually good enough? And there's no single metric that's going to capture all desirable properties for these models. There's a big trade-off between false positives and false negatives. So it's much better to say to a patient who isn't going to develop sepsis that they may develop sepsis than the other way around, when the implications could be much more serious. So in training, it's important to consider this case where it may be better to try and actually improve one rate over another rate. So I'm researching data from hospital wards, which I've mentioned briefly, but ward data is typically sparse and maybe more sparse than other hospital data. So if I have a lot of input features, then there won't actually be maybe measurements recorded for all of them at one time. Typically, in a ward setting, you'll have nurses walking around and taking these measurements by hand and then uploading them to some database. So there's a lot of irregularity in the measurements, as opposed to a patient who's maybe in the intensive care unit where they are hooked up to certain sensors that are monitoring them over the whole course of their stay there. But what we can do is actually utilize this irregularity. So I know that the gaps in this data are meaningful because if a patient is deteriorating, then they're going to have more regular measurements taken, and stable patients are likely to have less measurements. So I can include this within the stages of feature engineering that I'm doing, or within the actual training process of my model to try and encode some meaning between these data points. So finally, I'll talk about my own research. So I've only been doing my PhD for a few months, so it's not in massive detail, but I'll just try and go over like a nice overview of what I've been doing. So I've been researching time series classification for sepsis. So my data set is taken over the course of the patient's stay within the general ward. And I'm working with the Aneurin Bevan University Health Board. So they are based in Newport. They have 13 hospitals, I think, with a catchment area of about 600,000 people. And they're extremely interested in seeing if sepsis can be detected, because sepsis is extremely prevalent on hospital wards. I think it accounts for about 20% of global deaths, and its in-hospital mortality is anywhere from 30 to 50%, depending on the severity. And if I do have patient measurements, then what could be useful is having some predictive score for 3 hours, 6 hours, 12 hours before this sepsis event happens, to be able to start to treat those patients. So no specific antisepsis treatment exists. Instead, it's reliant on antibiotics, organ function support. Really trying to treat these patients as early as possible is what generates the best outcome. And this diagram here is just showing the kind of challenge of detecting sepsis. So infection can be caused by many different things. It's also hard to detect. And then if this infection is coupled with organ dysfunction, that's what's characterized as sepsis. So across the largest collection of time series data currently available in a repository that's commonly used, the best deep architectures are convolutional. So these are the architectures that are analyzing images, where within some model you have these kernels that convolve across the input features of an image or of a time series, and these kind of linearly transform this input data to extract features from it and to represent it in a different way that's useful. But these data sets within this repository are not as general as my case. I have generic ward data. They're much more specific with certain sensors that do a certain job. So what needs to be done is that I need to augment these high performance classifiers with a more detailed understanding of patients. So using some potentially unsupervised methods that could cluster these patients in a certain way and find correlations between different patient groups, which could be possible. I don't currently have access to patient demographic information, but it's certainly something that could be possible going forwards. And I just put this diagram in because I thought it was interesting to highlight. So the red model, inception time, is a deep learning model. So it's a deep neural network. And the yellow and the green line are ensemble methods using kind of statistical approaches and machine learning approaches. And just the training time between them, there's a huge discrepancy. So these deep models are more efficient. It can be trained on a larger data set in 16 minutes. And this rocket method that can be trained in 10 seconds utilizes this convolutional approach, but by just generating completely random convolutional kernels, and by convolving such a large amount of them, still actually generating very, very good results in a fraction of the time, which is why I've been focusing on convolutions. I think that they could be extremely useful and efficient as well. So the second part of my research is looking at generative adversarial networks. So a large problem of my data set is that it's highly, highly missing. So if I did want to get hourly measurement intervals for ward patients, then my data set is about 80% missing. which is not good enough to train a model. So what I can do is use these interesting generative architectures, which have two neural networks kind of battling each other during the training process, where one generates fake data and the other one gets as input fake data and real data and tries to determine which is which. So you might have seen these generating scarily accurate images, maybe of faces, and they do perform very well. On the image domain, we have extremely good data, but trying to translate these to a temporal domain has its own challenges. So why do we want to do this? If we do impute better missing values, so typical imputation methods could be taking the average value for some feature, maybe using 0 or using the average of its neighbors. But if we can actually learn kind of the whole probability distribution behind a data set, then we could impute much better values. The current models that are in literature only really perform well for lower missing rates. So less than 50% is probably even a push. They're often tested at kind of 20%, 30% missing, whereas my data set is much higher than that at 80%. So this diagram here is just showing that given some data set, you could get a generator that generates imputed values and a discriminator that tries to figure out, okay, which of these values were missing and which of these values are real. So they do work, but this model specifically is not designed for this high dimensional data that I'm using. I have lots and lots of features, I have lots and lots of records. So how can I actually utilize all of the data I have? So one approach that I've been using recently is called MISCAN, and it uses two of these generative architectures, one to generate this fake data and one to actually generate the distribution of masks, so the distribution of the missing data. So you're both learning the underlying distributions of the original data set and the underlying distribution of the missingness as well. And you can see in this diagram for the MNIST data set of handwritten numbers that given a 90% missing rate or an 80% missing rate, where each pixel is independently assigned a missingness based on some probability, that it can learn this underlying distribution and generate fairly good handwritten digits for only having 10% of the input data available to it. So in the top is just showing in gray the data that is missing, the middle is the output of the generator, and the bottom is the output of the missingness generator, so the representation of what's missing, which I think is very interesting how well this works. But as all machine learning researchers are aware, this handwritten digits data set is not particularly challenging to infer meaning from. You're not getting much variation in what looks like a 7 and what looks like an 8. So trying to convert this to my domain of time series features has been more challenging. So the current performance is extremely poor. The generation is not great. So what needs to be done is to encode some more relationship information within the data. So before I'm inputting the time series into the model, or also within the model, can I encode some important correlations? Can I do some unsupervised clustering to pick out certain classes of patient? And right now it's challenging because I don't have demographic information, but I have other data sets available to me with that information in place. So I'm just trying to figure out how to actually make these generators better and to use them in a temporal domain. Because another challenge is also when this data is highly missing, when we have 80%, 90% missing data, does any temporal relationship exist anymore? Does one time series, does the time element actually have any kind of meaning? So my current approach is looking at feature engineering, but my last few months have been spent kind of implementing and validating these techniques. So I'm now at the stage where I'm kind of augmenting them and putting my own kind of ideas into the algorithms. So yeah, thank you for listening. Here's some references. If anyone has any questions, I'll happily answer.